This example builds on top of the previous example of the Atwood machine. There's no pulley really, but again, we have a rope that goes over a tree branch. On the left side, we have a 10-kilogram monkey climbing up that massless rope. On the right side, we have a 15-kilogram package that is initially sitting on the ground. The question here is, what should be the acceleration of the monkey to be able to lift the package off the ground? We're going to assume no friction here between the rope and the tree branch up top. Somewhat of a crude assumption, but nevertheless necessary to keep the problem simple. So the first thing is to realize that in order for us to lift the package off the ground, or monkey to lift the package off the ground, the tension in the rope on that end must exceed the gravitational pull on the package. But it doesn't have to be constantly that larger than the gravitational pull. It just has to exceed it, and for a very brief time period just to get the package going. And after that, all we need is the tension to cancel the gravitational pull, because we have Newton's first law ensuring that the motion of the package will be kept in the absence of any net force. So we see that all we need is just a little bit of an acceleration to lift off the package, but after that, that package can be rising upward at a constant speed. So here I'm going to write down that the acceleration of the package will be 0 during the portion of the process when I'm going to focus on and solve the problem for. I'm not going to look at that first instant when I do need a little bit of a push beyond what is necessary to simply offset gravity. And also I'm going to assume that once the package has started moving at a constant speed or no acceleration, it has lost contact with the ground. So I'm not going to consider any normal forces here in its free body diagram when I draw the vectors for the forces. Next is to recognize that monkey and the package are not going to have the same acceleration. Unlike the previous example of the Atwood machine, when we had two objects and they were tied to a rope, so the rope effectively coupled their motion and forced them to move the same distance with the same velocity with the same acceleration within any given time period. Monkey here is free to climb up, down, jump, let go of the rope, and because of that, it is independent of what happens, somewhat independent of what happens on the other end. So we can't really say that the accelerations are the same. I will have no acceleration for the package, and I will probably have some acceleration with which the monkey is climbing up. I will mark this on my diagram here as AM, and I'll choose its direction to be upwards. And finally, the fact that we're going to work with massless rope and no friction up in the tree branch, and the rope is still not it's still inelastic, it doesn't stretch, ensures that the tension on both sides of the rope here is still the same, just as in the Atwood machine example. So with that, I'm ready to start drawing the vectors for the forces and applying Newton's second law. Let's start with monkey first. Here's the gravitational force, pulling it downwards. And that's pretty much it. I see all the vectors again aligned in the vertical direction. So I'm not even going to bother drawing a coordinate system. I'm going to jump directly and write the y components for all the vectors. So there's a Newton's second law for the monkey. We're going to focus on the y component here. All the y components have to add up to the mass of the monkey times the acceleration of the monkey. In components specifically, this will look like that. Minus the mass of the monkey, g, plus the component of the tension, Ft, has to be equal to the mass of the monkey times the component of the acceleration plus a. Here, the question is what's the acceleration of the monkey, but I still don't know what the component for the tension is, so I will need an extra equation to get to my answer. So because of that, I will need to go to the package, and I'm going to apply Newton's second law for the package. But before that, let's draw the gravitational force on the package downwards. And that completes my free body diagram. Remember, we're not drawing any vectors for the normal force. We're considering the package has already lifted off the ground, so it has lost any contact. So the equation here for the y components will be all the y components have to add up to 0, because once the package has lifted off the ground, remember, all we need is just to maintain a constant speed. It's already moving on its own due to Newton's first law. This equation here is going to be very simple. The component for the gravity is going to be minus the mass of the package times g plus the component for the tension Ft has to be equal to 0. And so here I can see that the tension, the vertical component of the tension will be simply equal to the product between the mass of the package and the gravitational acceleration. With that, I can go back to my first equation and I can actually solve for the acceleration of the monkey. From here on, this is just a simple algebra here to solve the equation and get the answer. Minus the mass of the monkey times g plus the tension, which I just determined, it's equal to the mass of the package times the gravitational acceleration has to be equal to the mass of the monkey times the vertical component of the acceleration of the monkey, which is plus a. With that, I can divide all terms by the mass of monkey and factor out g, and I can see that the acceleration, the expression for the acceleration is going to be equal to the difference between the two masses, the mass of the package minus the mass of the monkey, divided by the mass of the monkey, everything multiplied by g, which is the 9.8 meters per second squared, the acceleration due to gravity. And numerically here, once we place the package being 15 kilograms and the mass of the monkey being 10 kilograms, we see that the acceleration will be 4.9 meters per second squared, which will be our answer to this question.